invitation. So it's also a joint talk with Semyon, a blackboard talk. I would like to start with an explanation of the origin of the model. Also, this part, essentially appeared in a talk of Moro on Monday, and there is of course a significant overlap with what Dima was saying. So, we are talking about models for the fractional Hall effect on a torus, and this case has a particular charm because on the one hand side we benefit from the model, from the methods of algebraic geometry. However, genus 1 case, and it is the case when we have a complex torus, and the complex torus is a quotient of the complex plane modular lattice. Well, this case is fairly explicit, and maybe also the models we get here are closer to mainstream models for the fractional Hall effect happening on a plane. As already mentioned, so we have to choose a Hermitian line bundle, and the way to get it runs as follows. So I consider a particular function phi of z. I also choose a natural number, and I choose a continuous parameter, a point of C, and in this convention A and B are real. So attached to K and to Xi is a holomorphic line bundle. And what I have here, so I abbreviated by psi of z, it is a so-called factor of automorphy. So the outcome is a holomorphic line bundle of degree k on my torus E, and its description runs as follows. So I start with a trivial line bundle on a plane. So C has two roles here, so the base and the fiber, and that's why I separate my notation. So now I describe my torus as quotient of the plane, and my line bundle is obtained from C times V, imposing the following equivalence relation. I identify the point ZV with Z plus 1V, and it's also equivalent to Z plus tau psi Z times V. So
you mean ZV is equivalent, who is equivalent, or any of them, right?
Yes.
Okay. Mm-hmm.
Well, and the design of this function psi is so that, this relation indeed makes sense. And, a statement is that any holomorphic line bundle on a torus of degree k admits such a description, with k being the degree and psi basically uniquely different.
Psi, I don't have to know what it is. psi of z?
Well,
Psi.
it's above.
No, psi. Psi of
Psi,
it appears.
you mean this?
No, no, psi.
Well,
Oh, it's explained below.
it's
Oh, I didn't see that.
Yes. All right. So in this notation, it is easy to write the space of smooth sections. So these are functions, well, which are smooth and which satisfy quasi-periodicity conditions dictated by this equivalence relation. So I want it to be periodic with respect to shift by one and quasi-periodic with respect to the shift. Okay, so I defined a line bundle on a torus. So now I would like to define a Hermitian metric. And it's again a very explicit thing. So I take the function, well, which is given by some quite concrete formula. So here I believe I explained what is t. T is the imaginary part of tau. So y imaginary part of z. So what is well, the meaning of this definition? So for any smooth section, I define the length of my section at the point z, well, as usual length times h of z, and the obtained function is invariant under translations by 1 and by tau. Well, which means that for, well, any section f here, so for any point of my torus, I have well-defined lengths of the section, which well, allows to conclude that L is a Hermitian line bundle. So this structure of Hermitian line bundle allows to make from the space of any local sections, also from the space of global sections, a Hilbert space. So I define the scalar product, well, in an obvious way. So here I have a well-defined function on a torus, and I can integrate the corresponding two form, and it allows to proceed from S to a Hilbert space of sections of my line bundle. In the usual way we proceed when we introduce L2 of M. Well, next, well, one can see immediately that we have an operator acting from S to S. So since my factor of automorphy is holomorphic, taking Planck's differential operator preserves both conditions. And this operator also admits an adjoint, so it's a pleasant computation. So the exact form of adjoint actually does not meta. And so combining these two operators, we get a magnetic Schrödinger operator. Well, describing quantum mechanical behavior of a charged particle in a magnetic field on a torus. So this operator is, well, up to multiplying with 2 and some shift, just the Bochner Laplacian of the holomorphic remission line bundle LH, and one see immediately from the definition the description of the ground state. So ground state is obviously the kernel of d bar. So it is the space of holomorphic sections of my line bundle. Well, and one peculiarity of the genus 1 case is that we can explicitly write down the basis here. So we can, so the dimension of this space is k by Riemann-Roch, and we can write down the basis in terms of theta functions with characteristics. So, and let me also recall you the definition of theta functions with characteristics, because we will also speak about multivariate theta functions later on. So they are given by some explicit series. So with some of the exponential terms. Well, the assumption that the imaginary part of tau is positive guarantees convergence of this series. So it's one of the reasons why we want actually this assumption, which I forgot to write. So it's a good opportunity to say it again. All right. So now I would like to proceed to a description of many-body wave functions.
So, can I ask you a question? Yes. So in that space, in the ground space, you're assuming C, the character, to be trivial because it doesn't appear on the theta function.
Ah, you're of course right. So it comes here. Ah, okay. So there is of course a dependence of. Thank you very much. Right. So now I would like to proceed to a description of many-body wave functions on a torus. And the starting point is a fact about theta function with characteristic. So it has a unique zero. At point 1/2 plus tau half plus a tau plus b. So a tau plus b is my xi. All right, but of course unique modulo the lattice. But as a section of line bundle, so there is a unique vanishing. And of special interest is the case when both A and B are 1/2, because we see from here that theta z vanish at the lattice points. But it also can be checked that in this case we get an odd function. Well, which will be of relevance in what follows. So now, we understood one particle case. So let us accept that our particles can move on the torus quantum mechanically, and I would like to come now to, well, known descriptions of particle wave functions. So, my next topic is a presentation of a formula which appeared for the first time in a work of Haldane and Rezai. In 1985. So to present you this formula, so let me fix to natural numbers. So n will be the number of particles, and xi is a complex parameter. So now for any j between 1 and m, I would like to introduce the following function n complex variables, which is parameter dependent. So, and I would like to express parameter dependence by the upper index. And this function has the following structure. So there is one term which is product over all pairs pi smaller than q. So my theta function are introduced here, well, products of z power m. So far there is no dependence on psi here, and on j as well. So it comes in the second term. So W, well, is the sum of all the i's. And now for later reference, so I would like to call this term delta m, and this term I call psi j xi depending on v. Well, so it is a definition due to Haldane of Rezai, which generalize expressions for the Laughlin wave function. So one can ask question about the meaning and the origin of this thing. So I'm going to come to it, well, later on. At this moment, let me draw your attention that, well, if m is odd function, so the entire wave function is antisymmetric, and for m even, we have a symmetric wave function. Now I would like to proceed to the next model, generalizing this.
What do you want to do now with these beautiful functions?
I will just be patient. So it will, of course, I want to do something.
Yes,
I would like to give a meaning on that, but well, please give me a chance. Proceed to it. Right. So there will be a generalization, and then I will give a meaning to the generalization. So to generalize, I take another parameter g, and another parameter of the model is a symmetric matrix with integral coefficients, which has to be positive definite. So now I would like to proceed to...
G has nothing to do with the genus now.
No.
They remain on
No,
the
but,
torus.
well, in a sense, G in Dima's talk is a dimension of the Jacobian, and here G will be also the dimension of some higher dimensional torus. So, in principle, so this matrix can be fairly arbitrary, but of special interest. Well, it's a case where when K is the matrix of the following form. So on the diagonal I have M, and all of diagonal terms are M minus 1. So why I'm saying of special interest? Because some part of my results, so with Semyon, well, will concern only this special case. So actually, so this matrix, so I like this matrix because it is a source of natural examples for a linear algebra course. Well, which cannot be so easily defined, so if you are teaching linear algebra, you can make notes. And with a high probability, so you cannot find these properties via Googling. So first of all, it is easy to see that this matrix has eigenvalue 1. So with multiplicity j minus 1, because if we subtract 1, the rank is 1. And it's also obvious that the column 1, 1, 1 is an eigenvector, with the eigenvalue, the sum of the all horizontal entries, and these are gm minus 1 plus 1, and the product of eigenvalues is a determinant. So we have a formula for the determinant of this matrix, and we also see immediately that it is positively definite. So moreover, so any integral matrix defines a map of 3 abelian groups, and this quotient, which I will denote gamma, is always a finite group of order determinant delta, so it has nothing to do with a special form of this matrix, so it's a general fact. But for this matrix, this finite abelian group is cyclic, so which is again another fun exercise in algebra. Now I would like to proceed to the definition of wave functions of Kashiwakuri and Venn. And so the definition in principle applies to arbitrary symmetric positively definite matrix, but well, from didactical perspective, I'd like to define it only for the special case. Also, Van was insisting that the special case is insufficient. So, the structure of these wave functions will resemble, well, this form. So there is a discriminant term. So maybe I have to say, well, we are now talking about multi-layer model of our particle systems. And we have G layers. So G is this parameter. And for this special matrix K, so the model says that there are n particles in each layer. And for general K, actually, the matrix K dictates the way how the number of particles is distributed among layers. But now let me give you the expression. So these are, well, formula which looks like heavy at the first glance. So there is, I take product of all layers and then of all particles within a layer. And I put everything to the power m. And there is another factor where I take now the product.
Yeah, just to make sure, you really want different layers or in the same layer?
I'm in the same layer so
But
far.
then you need to change
K and
indices.
Q. Q. You know,
Yeah. So
Q. No.
K below and P above.
Like,
So, and now, well, I go.
range, but,
You mean the upper index is the number of the particle, and the
Well-
lower index is the number of the layer.
yes.
Yes. But I'm not yet done. So there is another factor.
Sure, but just,
You have to understand the notations.
yeah, it's a strange notation probably, but
Yeah, used to be P downstairs.
Well,
Now we have.
so now I'm going over different layers and through all particles in each layer. And well, it is my generalized discriminant. And for general matrix K, well, so it will be analogous but even more heavy. And now I want to define an analog of this. And here, well, J becomes an element of my finite group, and parameter psi is now a vector of C power G. And my theta function becomes a multivariate theta function. But it depends on only on the center of mass. So, all right, so what is my W? So W is again a vector. So a component of this vector is a sum of coordinates in my layer. And so the wave functions of Keskiva-Curie and Venn, well, are products of the discriminant. So and well, this goes. Well, for the sake of completeness, I also need to define the multivariate theta function. So it is analogous, well, to the definition in the to the case of one variable. So for the definition of multivariate theta function, I need a symmetric matrix with positively definite imaginary part, and it is again given by a series. So this definition can be found in the work of Keskiva-Curie and Venn. And let me conclude, well, this part of my talk with the following remark. So for G,
Question: this J should be divided by something, as in the psi expression.
J here.
Yeah, it used to be divided by m for.
Right, but it was divided by m because I was working with a finite group. And here, so I do not want to divide. So for j equal to 1, we recover wave functions of Haldane and Rezai. So for G at least 2, I have to make a remark that, well, the constructed functions are neither symmetric nor antisymmetric. So, and I have a, yeah.
Just one question. To be clear, gamma is the quotient group of k minus 1 ZG mod
ZG.
Okay.
Or the same ZG modulo, the
Right.
image of K.
Okay.
So I have a senior physics colleague who says that whenever somebody will tell him that the wave function of electron system is not antisymmetric, he will stop listening. So I don't know what is the mood in this audience. So in principle, so if you do not like this assumption, so you can take one layer case, but
Is it still symmetric or antisymmetric within permutation of particles in the same layer?
Yes.
Sure.
No, that's it.
I mean, the others are distinguishable because they belong to different layers.
would be also my opinion, but yeah.
Fix is actually simple. Fix is simple. You need to add the spin degrees of freedom, which are going to be, say if G equals 2, you're going to say it's this wave function times up, times down, and then you antisymmetrize everything. But that's a way to compact all this information. So this is not symmetric, but the full wave function after you done what I've said is antisymmetric, and there's no problem.
Okay, but now, of course, the question arises about the meaning of these expressions. So why do we call these functions wave functions? What is the meaning and what was actually the logic to introduce them? And I would like to explain it now.
But the summary is those functions were written on a sphere, and now and you put it on a torus, right?
It's not my invention, so it's literally can be found by Haldan and Reza.
And what is your?
I have not came to that yet. Yeah, so far.
Because I remember they simulate on the torus, so they must be written on a torus.
No, so our contribution will come, well, in the third part of my talk, and the third part of my talk starts.
Maybe you announce it.
Huh?
Maybe you announce it before. That's what he
Well,
said.
I'm going to do it.
It's like buying railroad tickets. First you pay and then you read the terms and conditions.
All right, so now I would like to speak about the result. And the result is about properties of so-called magnetic vector bundle. Well, and the variant of that was also the point of Dima's talk before. So I introduce for this a space So altogether I have G times n components, and on this space I have a line bundle. L.
Why do you have equally many particles in all the layers?
Why I have what?
Equally many particles. The n appears to be the same in
sorry,
all the
because
layers.
I'm working with this special matrix, which takes it. So if I allow more general K, so I can write n1 up to ng, but then on this vector n1 to ng will be a constraint. But I feared that, well, this formula is heavy enough, well, not to fight for a general form for it. And on this space I have a line bundle, which I construct in the following way. So on each individual component I have a line bundle of degree delta n. So delta is determinant of K. And well, there is continuous parameter entering here.
This is external tensor product?
Yes, what means that I have a line bundle on each factor, pull it back to X, and I tensor all such factors. Okay, so and of course it is a Hermitian holomorphic line bundle on X, which also has a Bochner Laplacian, and this Laplacian describes ng particles without interactions. And now I introduce a divisor, and this divisor is given by the matrix K. And for the special matrix case, this divisor is just more convenient to write. So I consider diagonals, running over the layer and running for components inside of the layer, or I run through different layers. So I have a line bundle, I have a space, I have a divisor, and the following lemma, which essentially goes again to Keskivakuuri and then says that the space of the wave functions is nothing but the space of the sections of the line bundle I defined here. So I consider the ground state, but then I impose vanishing of wave functions along all diagonals with orders specified by my matrix K. So it's a lemma of Keskivakuuri and Venn, and this space has dimension delta. Meaning that these functions are linearly independent. So, and now let me state the main result. So, main result. So, consider a complex torus A self-product of my torus G times. So if I like to write it as a torus here, it's a description. And in the theory of abelian varieties, so if we have a torus, then we have also a dual torus, which is the manifold of all line bundles which are topologically trivial. But in this concrete case, so this variety is isomorphic to A itself. Well, and now let me formulate the main result. So we have this vector space is depending on parameter xi, and I let my xi to be my dual torus. And then the statement is that there exists a natural holomorphic permission vector bundle here.
So,
Yes?
do I understand this correctly? Apparently every layer has its own fluxes.
Yes.
But that's sort of very unphysical.
Well, I will comment it in a second. So it's convenient to assume theoretically, but if you do not like it, there is
I
a way
don't
to
like
avoid it.
it.
Good, I also don't like it, but Let me state the result.
Yes.
I will be happy to comment. So there exists a natural holomorphic Hermitian vector bundle B on my torus, such that its fiber of xi
Yes.
well, and here there is an impossible didactical issue. So it's very hard to convince physicists that it's non-trivial to construct such a vector bundle because, well, you see a vector space, you can vary it analytically, and it gives you a vector bundle you wish to want. But the naive approach to say that you compute monodromies of these functions and they give you factors of automorphy of your bundle is a wrong point of view. So it just gives you a wrong result. So and there is indeed an issue to define it, but believe me that there is a difficulty to do it. But I would like to comment some properties of this bundle. So it is simple and semi-homogeneous. So you're not supposed to know what is a semi-homogeneous, but a property is interesting. So for semi-homogeneous vector bundles, the total Chern class is expressed via the first Chern class. So this vector bundle has higher Chern classes, but they are all expressible via the first one. And for the first one, we have a close expression. So the first Chern class is a two-form, and I can write this form concretely in terms of the so-called adjunct matrix of K. So what is the adjunct matrix? So it is almost the inverse matrix, but up to determinant. So it has integral coefficients. Now, so if my matrix K is special, so another nice property happens in this special case. So the constructed functions of Keskiva-Curie and Venn are orthogonal to each other, and the corresponding Gram matrix well, is a multiple of the scalar matrix. So it is some function of xi times the identity matrix, which in particular implies that the canonical Chern-Weil connection of the constructed bundle is projectively flat. It's projectively flat. Well, and the final point why the special K matrices are so nice. So we can embed diagonally my torus into, well, the space full space of fluxes, and I can restrict my vector bundle on this diagonal. And this bundle remains simple. And one can also compute its topological invariance.
It's 50 minutes.
I know. So I am always done. So let me better say degree of this restricted bundle is minus g. And if you consider the slope of this vector bundle, which is the fraction, then it is minus g divided by g m plus 1. So, restricting to such diagonal, so it actually means that for each layer we have the same flux. And this fraction is, well, the filling fraction of all conductance. And actually it's a whole charm that we derive this number in such a way. Well, however, just to comment, so I think both physically and mathematically it is advantageous to allow each layer to have its own flex. And I wanted to negotiate about extra time, but I fear I'm not in a position to negotiate. So I just want to say that the key technique, well, to construct and study B is given by the formalism of Fourier-Mukai transforms and derived categories of coherent sheaves on abelian varieties. So, and using this technique actually makes possible to derive in a relatively simple way all these properties. So it really simplifies the story to allow flux in each layer, even to prove this result. Well, and I believe I really have to stop now. Thank you very much.
Thank you. May I quickly ask, so from the computational point of view, you computed these direct Hall conductances,
Yes.
Which is coefficients of this K.
Yes.
Was it not known, this K joint matrix?
Well, what should I say, Semyon? Was it?
C1 was known, but full Chern character was not known.
Well, there was.
This bundle is projectile flat was not known.
Well, that's for sure. That's for sure.
That this bundle has higher Chern classes and that it's projectile flat. So the idea is that all good quantum Hall states should be projectile flat.
Well, of course.
We should all check them if they are good or not.
We'll talk about physical meaning of that.
Well, of course, there were contributions by Venn, who studied it very intensively, but I believe, well, everything what is written on this blackboard is mathematically new.
So, questions?
So this is all about non-interacting electrons.
Well, but somehow imposing this condition, that's, so actually what we do here, we just...
I mean, it's not, it's an ansatz.
Yeah.
Right, well, but Laughlin also made an ansatz, right?
Laughlin
Yeah,
is a
but-
particular case of this.
But do we now understand why this has something to do with what would really happen in a material if I started from the basic Hamiltonian of interacting electrons?
Well,
I don't understand what this is about.
well, so here, basically, you have an exactly solvable model. And that's why algebraic geometry comes here. And
This is a wave function. It solves which problem?
So with the correct pseudo potential, it's the exact ground state.
No, but
well,
Okay, next question. This is discussion during the dinner. So, please.
So on the plane, there would be it's a Hopper state, right? There's a single ground state on the plane, and with this K matrix, you would have SUG. It would be a singlet under SUG. Now on the torus, you have a multiplet. Is that a bunch of singlets under SUG, or is that a non-trivial irrep of SUG, or
SUG, what is SUG?
symmetric unitary group? It's going to act by permutation of. So it is a fact that on the plane, that's a singlet under.
Well, so what I can only say is that I'm aware of the paper of Halperin and believe so he was the first who introduced these multivariate wave functions.
Yes.
It's a multi-layer, and it's a fact is that it's invariant under.
It's again the question about symmetry between electrons.
Yeah, it's about the symmetry under. Sorry, no.
You can anti-symmetrize this wave function.
No, the full wave function is, let's take g equals 2, so you have spins up or down, half of them are up, half of them are down. So the wave function as written here is a component where the first n electrons are up and the last n electrons are down. But the full wave function, you take all this, including the spin, and you anti-symmetrize. That's anti-symmetric, and this is SU2 invariant.
All right. So
What happens on the torus? But maybe it's more a question for that 93 papers. So.
when you identify the identification he made in the end makes that anti-symmetrization.
I mean, I know it's anti-symmetric. The question is now you can act with SUG by permuting the layers.
Yes.
It's a global symmetry of.
Also, I mean, the edge states have this beautiful SUG current algebra. That
Yes,
is
so
here.
it should also act on the ground state, on the space of ground states. But
And since we
I think the question is the representation of the symmetric group SG. There are G layers, so there is a symmetric group SG acting that should act on this vector bundle B.
not SG.
What is the representation?
SUG.
So here there is, we are using the action of the Heisenberg group actually, but not we are not aware of SUG so far.
okay, we can. I can tell you on the plane and.
Yeah, please.
I mean, is there actually a proper Hamiltonian? Because I saw that there's a paper by Haldane from 2015 or something like that where it says the ansatz has to look different, has to be some
Well,
very
no, of course there is. So because you have a Hamiltonian for each particle, and you just
Let me ask, so you quoted this 85 paper, but now I saw that 2015 there was another paper by Haldane saying it has to be modular and invariant if the right wave function solves it on the torus. So he introduced some sigma function rather than the theta function in this ansatz. So I'm wondering if you could comment on, because I guess you know that paper probably better than me.
no, we have not looked at that. Talking about the Hamiltonian, it's just the sum of individual Hamiltonian. So it just and particle Hamiltonian, no interaction, but instead of interactions we make this Laflin's ansatz.
This is interaction.
Okay, so it's one can rephrase it like that.
One last question.
A very simple question. So, does this Venn Hamiltonian on the Venn wave function on torus works for other K matrix?
How it looks for other K matrix? Well, so you have here instead of M, M, G, M, K, well, for it's a case diagonal matrix. So here you have M, KL. But also the number of particles will then, depend. So you have K here. So now you have here and K and L.
The issue is the central mass piece because each particle will see the total zero will sum to zero, right? This is a constraint for the many-body wave function to be valid.
Well, so there will be then constraint on the number of particles in each layer, so controlled by K.
Okay, so let's thank speaker again.